This time on Sailing Poor Richard, we LiDAR the keel and produce a 3D computer model so we can analyze the performance to compare the winged bulbed keel to a straight keel.
So someone on Facebook reminded me that I can always use my LiDAR to do some measurements and stuff. So I have wanted to analyze, since I'm a hydrodynamicist in some lives, an aerodynamicist in others, associate director of the waterfront in some, marine engineer in some. So anyway, what I want to do is I am going to LiDAR my winged keel on my Hunter 35 Legend, which I find to be quite a great sailing boat. This thing is just fine. I'm going to find out. Compare it. I'm going to compare it with a deep keel. But in order to do all of that, I really kind of need to know, what section is it? What are the dimensions of it? How does it model up, actually? These are all questions that I'm going to answer with a Rhino model built from my LiDAR data. So, here we go. Here we go. We are now looking at what happened here. So what we did was we made the keel scan. Let's go there first. I turn off surfaces and turn off the longer. Okay, this is the keel scan that we made. This is from a better LiDAR. I used the advanced LiDAR. It did very well and got a little bit more detail, except it messed up around the leading edge and it was thicker, just like the other one. So I measured the thickness of the keel and all the other dimensions that are shown here. And I corrected the mesh created by the LiDAR. Okay, so let's go to surfaces and see what that really taught me. We're going to turn off the dimensions and the hull and the ground, and that should be on layer longer keel. So I'm going to change that real quick. Okay. So now what we have here is I found out from comparing the real section to the LiDAR section that it is a NACA 64 AO12 with about a 1% thicker trailing edge. Okay, but I can do that with my foil generator programs. I'm using hydrofoil, okay, and then importing it into Rhino. Everything is derived from that NACA 64 AO12. Okay, even the bulb and the little winglets that are on the bulb. Okay, so my next step is to figure out what the weight looks like. So I calculated the volume and the CG, and then I pulled that into Excel, right? And I looked at, well, the reported weight of the keel, or the ballast, is 4,800 pounds. Well, we're a little light, but I don't have the bottom portion modeled completely yet. So I expected it to be a bit light. If I go straight to a 6.5 foot draft, then I get 4,800 pounds exactly, which is pretty interesting since the reported ballast is 4,800 pounds. Okay, so then I calculated the Reynolds numbers. Really, this is my cavitation spreadsheet. We don't have to worry about cavitation because we're not going that fast. But if you are curious, cavitation is calculated by taking the atmospheric pressure plus the density times the gravity times the depth minus the vapor pressure of water divided by the dynamic head, which is 1/2 the density times velocity squared, if you're curious. Okay, I don't know how curious you are about that. But anyway, here's where it came from. And that's where we're going, okay? So, next thing I did was I compared these things, okay? So first we modeled something that looks like the various things we're looking at, okay? So we got the straight, deeper keel. Now this is modeled as if it's an airplane, okay? So the keel is from the center line out, and to calculate any kind of lift from this, we would just use half. But we're developing non-dimensionalized coefficients, so this works fine. It enforces a plane of symmetry along the center line, okay, which is like you've end plated it with the hull, okay? So you ignore half of it in order to do a comparison, okay? But you can see here it develops a tip vortex, which is everything develops a tip vortex that's lifting like that because it's displacing a fluid in a continuum, and it has to make that fluid up from the pressure side to the suction side, okay? You're making water or air go a different direction, and it has to be wrapped up, okay? Simple explanation of that. Now, that's the straight, deeper foil. We can compare that to a shorter foil without winglets, okay, as our control, right? And you can still see the very elliptical lift distribution here, okay? And now we're going to compare that to our winged keel, right? With approximately 3 to 5 degrees of leeway, which is a typical race boat. There's 3 to 5 degrees of leeway, okay? So what you can see here right away is those wingtips inhibit the tip vortex. Okay, we're now at 3 degrees of incidence, 3 degrees of leeway, if you will. And notice that the lift curve is almost straight across. Well, that really it means that you're using the tip to more effect because you've end plated it and stopped that leakage, okay, from the pressure side around to the suction side. Okay, it's more pronounced at 5 degrees. So this side is lifting outward because it's inhibiting the flow coming from the inside out, and this one is lifting inside because it's inhibiting the flow trying to come in, straightening, okay, which is exactly how winglets work. Looks to me like this is pretty well designed, but I couldn't include the dihedral on that, just in the way this model works, okay? But what this does for us is produces what we call polars. So now we're going to go to polar view. Okay, now we're in the polar view, and we're looking at the incidence of the winged keel at 3 degrees of leeway to 5 degrees of leeway. Okay, 3 to 5. And we're looking at the lift curve slope here. Let's go to graph 2 first. That's very interesting. Even though it's smaller, the winged keel is producing far more lift than the longer keel and far more lift than itself without the winglets or the bulk. Okay? That's a pretty significant result. So now that's 5 degrees. This is 3 degrees. So what's that mean in the scheme of things? Okay, let's go back to all graphs and look at the straight, deeper keel at 3 degrees, okay? That's our operating point at 3 degrees. This is our operating point at 5. Well, look at the difference in the amount of lift for the same incidence angle. What that means is you're saving at least about, let's see, that's 2.4, and that's about 3. So you're saving about 6/10 for the same amount of lift, okay? The winged keel will produce a 1/2 degree less leeway. Well, the hull at a 1/2 degree more or less leeway would make up for a lot of that extra drag. And of course, then you look at these drag values on this. These are coefficients, right? So this is non-dimensionalized by the dynamic head, so and the area. Lift coefficient is going to go from 3 to 5 degrees. Okay. If you look at the straight deeper keel, it's going to go from 3 to 5 degrees. Okay, well, from 3 to 5 degrees, the difference here is like 0.00 something. You know, here we've got 0.0056 drag coefficient, and then here we have 0.0096. So there's a 40% increase in the drag at 0. But up here where we're actually using the thing, somewhere between 3 and 5, it's less than that. And for a given angle of attack, the winged keel is producing a considerable amount more. Okay, so let's see, where were we here? We're at 3. So now we're going to go to 3 here. That's a significant increase in lift coefficient from here to there. So that is going to equate to a considerable lower amount of leeway. And then the hull will produce less drag there. So the keel is producing more drag, but the hull will be producing less. Combine that with the fact that the Hunter has a very efficient rudder, and it depends on whether you're using the rudder to counteract some of the weather helm, producing a little more efficient side slip resistance. So in conclusion, I would think that what we're talking about is very, very minor. Now, let's look at the longer straight keel, okay, and where its center of gravity is. Because you have the lower bulb in the wing, okay, and that's heavy, okay, what's happening here is you only change the center of gravity of the metal parts, or the ballast, right, by 2.7 inches. So the riding moment hasn't changed that much either. It's slightly, maybe less stiff with the winged keel. But I'm betting once again that that's offset by the fact that this is lifting with a much higher efficiency because of that linear lift distribution. So what we're talking about is you probably aren't going to go more than about 4.5 degrees, right? 3 to 4.5, or 2.5 to 4.5, because of that added lift coefficient. And so, in conclusion, I say that the winged keel probably is a wash compared to the deep keel section. I've really always felt that the Hunter 35 beats to windward very close. I'm sure when you look at the GPS track, it's 50 degrees or 48 degrees or 45 degrees, but it sails very high, and I've never seen a deep keel boat sail much higher. It may be a little, but not a lot. The apparent wind angle is very narrow. The masthead fly arrows seem very close. They're at like 30 degrees, plus or minus, from straight ahead. It's a good sailing boat. And that's from a lot of experience. I mean, I've sailed Beneteau 49s, I've sailed FAR 40s, I've sailed FAR 30s, I've sailed the J29, the Evelyn 32, a bunch of different larger boats. And yeah, some of them sail higher than Poor Richard will. But boy, when it's clean and I just put it in the water, I've been very surprised at how well it sails upwind. So if you can tell the difference between a deep keel and the winged keel, really measurable difference, and it's not sailor error or sailor difference, I would be pretty surprised, really, in all. And it's going out on a limb, but you know, what's YouTube about if it isn't about being a little bit controversial? So, goodbye for this time on Sailing Poor Richard. We'll see you out on the water as soon as the winter time is over and we've got all our projects done. Next time on Poor Richard, we will probably be talking about changing our systems on board, installing the heater and doing all of the NMEA stuff and cleaning and oiling teak and all those kind of things. But for now, goodbye and have a really good Christmas season.